All right, you found the beginning of the gas laws unit. Gas laws is going to be like a standalone unit. This first couple of days, it's okay if you don't remember what you learned from before, because what we're going to get into is kind of new stuff. It's going to be very mathy. It's going to be equation oriented and not really based on chemical equations and chemical formulas until a couple days from now when we get into the stoichiometry of gases. So that is coming, but you've got a little break from it. What gas laws are based on is the kinetic molecular theory. Kinetic meaning energy of movement. Molecular referring to atoms or molecules. And it's a theory because it's proven, it's backed up by all of the data that we have, but we can't observe it at the atomic level, so we can't, there may be missing pieces. Definitely correct based on what we know, but could be missing pieces. The three assumptions of the kinetic molecular theory is first, all matter is made of tiny particles. Those particles we've been studying, those are the atoms and molecules. Second, these particles are in constant motion. There is an exception. The exception of this is absolute zero. Absolute zero is a name for a temperature. Absolute zero is the temperature 0 kelvins or negative 273 degrees Celsius. That is the coldest temperature that exists where all motion is assumed to stop, meaning molecular motion or atomic motion. So even atoms stop moving at absolute zero. It's calculated temperature, it's a theoretical temperature. Notice that it's pink, it's italicized, and it's underlined. It's also bolded. This is a vocabulary term for this unit. Make sure you can find it. You're definitely going to be asked about the definition for absolute zero. Back to our kinetic molecular theory, the third part of the kinetic molecular theory is that all collisions between particles are elastic. No energy is lost upon collision. Therefore, the total energy of the system is constant. What this means is something that we're not quite used to. When cars crash, there's definitely not an elastic collision. Energy is released, energy is absorbed in different parts, and the particles do not just bounce off one another and keep on going. So this kind of collision we're not really used to seeing, but if we think about gases and atoms, then it does make sense because it doesn't start randomly raining inside in a room. It would if when water molecules, which are in the air right now, if these water molecules, when they hit each other, when they slowed down, then they could eventually turn from a gas into a liquid and rain would happen. And that doesn't happen, so there's our piece of evidence that this statement number 3 is true, that the collision between the particles are elastic, that no energy is lost upon collision. This kinetic molecular theory helps to explain certain gaseous properties, like relationships between volume, temperature, and pressure. And that's really where we're going with this unit, is to actually solve math problems about these relationships between volume, temperature, and pressure. For example, one of the things that the kinetic molecular theory explains is the property of gases that they expand. When gases are introduced into an environment, they will expand to fill up the whole environment. They use these properties to kill people using mustard gas. If mustard gas just stayed in one place, then the soldiers would be able to just walk around it or step over it. Instead, the mustard gas expands to fill an entire area, and that's why it's an effective killing weapon. Diffusion of gases, a much more pleasant example, is if we think about scented candles. When you light a scented candle, that scent fills up the entire room as the gas diffuses. The gas will mix around the entire room until the entire room smells just like the candle. Those are two examples of applications of the kinetic molecular theory. Some more relationships. If pressure is held constant as temperature of gas increases, the volume the gas occupies will need to increase also. This is a direct relationship. So we can think about this if we think about balloons in the summertime. If we have our nice balloon right here, and we get it filled up inside of a nice cold grocery store, when we take it out into the hot parking lot, the balloon will grow until it pops. Why? Because when the gases are cold, they are one size. Once the gases heat up, they need to expand. As the gas expands, it usually expands outside of the parameters of the balloon, makes the balloon pop. Because both the temperature is increasing and the volume is increasing, we call this a direct relationship. Both of the variables are traveling the same direction at the same time. The opposite of that would be an inverse relationship. So if we have that same, let's say we have another example. We've got a water balloon, or a water bottle, plastic water bottle that's empty. If the temperature is held constant, so if we have an empty water bottle inside the classroom, as the volume in which the gas occupies decreases, so if we squeeze the water bottle down, here's my beautiful drawing of a water bottle. That's lovely. And let's say we squeeze it, so we're smashing the center in completely, making it have an hourglass figure. We have smashed it in completely. The volume has decreased. Volume decreased. The pressure will increase. Pressure increases, and that's how we blow the lid off of it. That's a fun thing to do. You should try it sometime. I'm a little bit too chicken to do it myself, though. This is an inverse or opposite relationship, so there's a name for that relationship too. Before we get to our first equation, we need to know some definitions. So STP is a term. STP means two things. It means words. In words, it means standard pressure and temperature. It also has number values associated with it. STP, standard pressure and temperature, is going to be 1 atmosphere of pressure and 273 Kelvin in temperature. This you need to memorize. So make sure you know what STP means, that it means standard temperature and pressure. Make sure you know the number values associated with STP. The STP is 1 atmosphere of pressure and 273 in Kelvin. Now, just for your frame of reference, just to familiarize yourself with degrees Celsius and Kelvin temperatures, room temperature is about 25 degrees Celsius or 298 Kelvin. So that's average room temperature. When the air conditioner kicks on and it feels super cold, then the temperature in the room is like 22 or 23 degrees Celsius. If the air conditioner breaks and it feels a little bit warm, it might be 27, 28, maybe even 29 degrees Celsius. 25 degrees Celsius translates into 298 Kelvin. And so, again, that's for your frame of reference. So you start to get to know these Celsius temperatures that we're pretty unfamiliar with so far because we live in America where we use Fahrenheit all the time. Pressures are also really important to know about. In most of our problems that we'll be doing, we will be using atmospheres as our pressure units. Atmospheres of pressure are normal, everyday, nothing special pressure of the atmosphere. This is the pressure that you're experiencing right now. If you round it to one significant figure, it'll be 1 atmosphere. Since we've been measuring pressure for such a long time, We have a lot of different units of pressure available for our calculating pleasures. These units are on the back of your periodic table, the back of the bottom of your periodic table. We'll have all of the conversion factors for the pressure units. Says something like this. So notice that 1 atmosphere, the 1 is permanently attached to the atmosphere, is equal to 760 millimeters of mercury. So 760 permanently attached to the millimeters of mercury, or 76 centimeters of mercury, or 760 torrs. 1 atmosphere is also equal to 101.3 kilopascals of pressure. So these are all just different pressure units. You'll see more than that on the bottom of the back of your periodic table. We are going to practice using these conversion factors. And before we get there, let's look at these. Up here's a primitive type of barometer. It's used as a different example in a different application, but here's the idea. This side of the tube is going to be sealed and vacuumed, so not open to the environment. The other side of the tube is normally open to environment, and this is the kind of barometers that sailors had on ships back in the early days of sailing, and they knew that the weather was changing if the barometer changed drastically. They used this to predict the weather sort of and know and prepare for storms as they arise out on the seas. So because we've been measuring pressure for so long, we have all these different units of pressure, and we need to be able to convert between them. So back to our conversions. We've got 800 millimeters of mercury. We want to convert it to atmospheres. So on the outside of our parentheses, 800 with a decimal point millimeters of mercury. Inside of our parentheses, we know we need to cross-cancel millimeters of mercury and turn it into atmospheres. From the back of the bottom of our periodic table, we pull the units, or we pull the numbers that are permanently attached to these units. 1 is always with atmospheres, 760 always with millimeters of mercury. 800 divided by 760, 3 sig figs, is 1.05 atmospheres. Pause the video and try the kilopascals conversion on your paper right now. Go. Okay, you're back, and 800 with a decimal point millimeters of mercury. There's 760 millimeters of mercury and 101.325 kilopascals. Yeah, you can do that because they're all equal to each other all the way across the bottom of the back of your periodic table. So 800 divided by 760 times 101.325 gives us 107 kPas. Next, we are talking about Boyle's law. Boyle's law is P1V1 equals P2V2. Boyle's law is on the back of your periodic table and disguised as the combined gas law. You've probably already guessed that P1 is the original or initial pressure, V1 is volume, P2 is a new pressure, V2 is a new volume. You'll need 3 of the 4 variables to solve the problem. So here's the combined gas law. If we cross temperature out of it, then we've got Boyle's law, P1V1 equals P2V2. Let's try and use it. So in order to use this, we're going to use the same solving strategy every single time. Here's our sample problem. A balloon is at 2.35 atmospheres of pressure, constant temperature. Original volume is 4.50 liters. Volume is reduced to 0.750 liters. What's the new pressure in the balloon? We'll make a table. The table is going to be the same for every single problem. We've got P1, T1, V1, N1. Pressure, temperature, volume. N is moles. Little m was already taken. It's meters. So we use little n for moles in our gas laws equations. We will fill out the table from the problem. So 2.35 atmospheres of pressure goes in for P1. Constant temperature, that means we can cross it out. The original volume of the balloon is 4.50 liters. If the volume is reduced to 0.750 liters, what's the new pressure in the balloon? Since the balloon is sealed, we will cross off moles because that's not going to come into play into this equation. Right now we only know one equation, so it's easy to choose that. At the end of this unit, we'll have 5 different ways to solve a problem, so that's why we're using the table. Next, we'll plug and chug. So the equation that we're going to use, since we've got 2 sides of the table filled out, is P1V1 over T1 equals P2V2 over T2. We crossed off temperature in our table, so we can cross off temperature from our equation. And we've got the equation P1V1 equals P2V2. P1 is 2.35 atmospheres. V1 is 4.50 liters. Whoops, ran out of room. P2 is what we're solving for, and V2 is 0.750 liters. So if I divide both sides by 0.750 liters, my second pressure is going to be, so 2.35 times 4.50 divided by 0.750 is going to equal 14.1 atmospheres. And that'll be my final answer with sig figs. Does this make sense? Well, my volume is getting drastically cut. That means my pressure needs to go up. It's like we're squeezing that water bottle again. So yeah, it goes up by a lot too. It makes sense. Second example, 25.6 liters of helium under some pressure. The pressures increase, calculate the new volume. We fill out our table, and our first thing we see is 25.6 liters. That's going to be volume 1. 25.6 liters. Second thing we see is 200.6 kilopascals. Third, we have 4.50 atmospheres. That's going to be pressure 2. Now, what we need to notice is that our pressure units do not match. So we are going to need to fix that right away. Let's change our atmospheres into kilopascals. So 101.325 kilopascals in 1 atmosphere gives me 456 kilopascals. All right. What we're going to calculate is the new volume. So that's volume 2. Whoops, that's a question mark. Temperature wasn't mentioned, moles not mentioned. Equation that we're using, P1V1 over T1 equals P2V2 over T2. How did I know that? Because 2 sides of the table are filled out. I crossed off temperature, so I cross off temperature. I'm ready to substitute. 200.6 kPa. 25.6 liters equals 456 kPa, and I'm solving for V2. I barely snuck that in there. In my calculator, 200.6 divided by 25.6, multiply by 25.6 divided by 456. So V2 equals 11.3 liters. Next, we've got Charles' law. So Charles' law is V1 over T1 equals V2 over T2. We've got constant pressures. We've got constant moles. And for this, temperatures need to be in kelvins. No Celsiuses will be allowed. We have a conversion factor for Celsius on the back of our periodic table right here, where we see Kelvin equals Celsius plus 273. And again, combined gas law, definitely on the back of our periodic table. And this one, we're crossing off pressure. So we get V1 over T1 equals V2 over T2. Example. Constant pressure, yay, cross something off. Balloon contains 20 milliliters of air, 20.0 ml. Temperature was 22 degrees Celsius. That is not going to do. So 22 plus 273 is 295.0. Because we need to add 273. Some ice cubes are placed on the balloon to cool the gas to 10. 10 is not going to do. We need to add 273. 273 plus 10 is 283. 283.0 Kelvin. And volume 2, that's what we want to know. So we're cooling down this balloon a little bit. We should see this balloon shrink a little bit. And here's our equation. P1V1 over T1 equals P2V2 over T2. We crossed off pressure, so we cross off pressure. V1 over T1 equals V2 over T2. V1 is 20 milliliters. T1, 295.0 Kelvin. V2, what we're solving for, 283.0 Kelvin, is V2. The math we're going to do, we're going to multiply both sides by 283 to get rid of it because it's on the bottom of a fraction. So 283 times 20 divided by 295 is 19.2. All right, one more example and we're done. In this example, we're going to fill out the same table again. So constant pressure, volume 900 milliliters. Temperature 15, we don't like 15. 15 plus 273 is 288. If the gas volume goes to 396 milliliters, what's the new temperature? Moles not changing. Equation we're picking, P1V1 over T1 equals P2V2 over T2. What are we going to cross off? Pressure. And volume 1, 900 milliliters over 288 Kelvin equals 396 milliliters over T2, which is what we're solving for. The solving strategy that you learned in math is the crisscross method. So that's what we're going to use right here. We've got T2, which is on the bottom of a fraction. We can't just multiply both sides by 396 and call it a day because our T2 is on the bottom of a fraction. We need to get it up on the top of a fraction first, and that's why we use the crisscross method. So what's connected with the lines is going to be our new equation. So we have T2 times 900 equals 396 times 288. And that's kelvins. 396 times 288 divided by 900 is going to be our final answer. Oh, almost our final answer. 127 Kelvin. But we want our new temp in degrees Celsius. So we convert it back, which is easy because kelvins subtract 273 equals Celsius. So negative 146 degrees Celsius is our final answer. All right, that's it. Congratulations. Woohoo!